Okay guys, right, last question, question 7. This is to do with circuits and circuit diagrams, so let's get cracking. So first thing, this is about a filament bulb, and you've done Ohm's law and the potential difference current graphs, and through a bulb it's an S curve. Normally you get a nice straight line going through the origin, but this time it's an S curve because the resistance changes. As it gets hotter, it increases, it gets hotter. So there's 2 marks for that. One's for this nice S curve here and here, and one's for the changing gradient. So lovely, there's a good starting point. Right, next then, let's have a look at the next bit of this. So this is a parallel circuit here, and it says compare the currents I1, I2 and I3. So what do we know about parallel circuits? What we know is that the current comes out here and it splits. So I2 and I3 added together gives us I1. But I1 equals I2 plus I3. Okay, that's how the current changes. So, what can we say about I2 and I3? Well, the question tells us that these are 2 identical filament lamps, so we can assume the resistance down both paths is the same, so we can assume that I2 equals I3. And there's your 2 marks, right? One for knowing that parallel, the sum of these paths is the total current. 1 mark is for knowing that those 2 are the same. Right, the next question is a calculation question. It says calculate the charge that flows through the cell in 1 minute. So, what information does it give us? Well, it tells us 1 minute. It gives us a resistance of 12 ohms, and each lamp has a power of 3 watts. So, I need to think about my equations. So let's just quickly jot down the equations that you've learned. You've learned 5 equations for physics, or you should have learned 5 equations, and this is physics and combined science. So these you should hopefully have remembered. This last one, by the way, P is I squared R, is a combination of those 2 combined together. So we won't worry too much about that. Right, what information's in the question? It gives me the time, which is 1 minute. It gives me the power, which is 3 watts. It gives me the resistance, which is 12 ohms. And it's after the charge, which is Q. So what equations do I need? Well, to find out charge, the only one I've got is Q is IT, and I've got T, so I need to find out what I is. What else have I got? Well, I've got P and I've got R. So P and R are there, and that gives me I, which I can use. So I'm going to use those 2 equations there. Right, so that's my starting point, those 2 equations. So, excuse me, what do I do first? Well, I need to start off with that equation there, which is P equals I squared R. And I'm going to rearrange that. I is going to be I squared, is going to be P over R, and so I can simplify that again to I is the square root of P over R. So all I've done is rearrange that. Then I can plug the numbers in. So that's going to be the square root of 3 watts, because that's the power, divided by 12 ohms. So break out calculator, and square root of 3 divided by 12, that gives me 0.5. So that gives me an answer which is 0.5 amps. Now that is each lamp. That's the current through each lamp. Going back to the initial part though, if I know the current there is 0.5 amps, I know the current there is 0.5 amps, the current going through the entire cell, and that's what it says, charge through the cell, that's going to be the sum of those 2. So I total is going to be 1 amp. It's going to be 2 of those. Right, what do I do next? Well, the next thing I can do is to use the Q is I times T equation. So the next bit here is Q equals I times T, which is 1 amp times, now the time is 1 minute, it said in the question, but I need that in seconds, so I convert that into 60 seconds. 1 times 60 equals 60. What's the unit for charge? That's coulombs, capital C or coulombs. Right, so where are my marks available there? Because this is a 6 mark calculation, which means we've got tons and tons of marks there. So, first things first is for that equation and rearranging it into that and getting the answer, which is that. So, if you get that equation and you plug the numbers in, and you get that 0.5, you've got 1, 2, 3 marks there. If you then work out that that is there are obviously 2 of those, and you plug that into here, you get the answer, which is 60 coulombs. So there's 6 marks there. Right, done. So last little bit of this then is another question about a circuit, and what this is saying is explain how the readings on both meters change when the environmental conditions change. What you've got to do for that then is not just state, but explain. So, first things first, right? What do we know? I'm going to scribble all over the question just so that it makes it a little bit easy to see what we're actually doing. So first thing we need to know is that that is an LDR. It's a light dependent resistor, so the resistance will change when the light intensity changes, and that's the environmental condition. Okay. What else do we know? We know that it's a series circuit. So the current here is the same as the current here, here. It's the same all the way around. We also know that if I were to put a voltmeter here and call that V-tote, and have a voltmeter here and call that V1, and make that V2, I know that in a series circuit the total voltage or total potential difference is V1 plus V2 plus dot dot dot. Right, there's anything else in there. So the sum of those two is the same as that. Something else. And I also know that the resistance in the circuit is going to be the sum of the resistance, so that should be an R, plus the things there. So I've got a resistance here, let's call that R1. I've got a resistor here, let's call that R2. The total resistance is the sum of those two, plus any resistance in the wires or any other components. So, excuse me. So, let's see if we can get 6 marks for this. Let's explain what happens to these two numbers when light intensity changes. So, first things first, right? The component is an LDR, light dependent resistor. So, as the light intensity increases, the resistance of the LDR decreases. Spot on. Right. So what? Well, this is a series circuit. If that resistance goes down, then the total resistance goes down. As this is a series circuit, R total equals R1 plus R2 plus etc. Right, whatever else is there. So, as the light intensity increases, because I was talking about it going up, then the overall resistance decreases. So what? Right. That voltage will not change. That cell has not changed. As the potential difference, aka voltage, from the cell does not change, and the voltage is the current times the resistance, if the overall resistance goes down, then that doesn't change, that number goes down, that number must go up. So the current must increase. So the reading on that ammeter must increase. So what have I done? I've talked about what that component is, I've talked about how the light intensity changes, and I've then explained or stated how it's changed that and explained that as well. So job 1, marvellous. Right, job 2 then. What happens to the voltage here? So let's go back to it again. Right, well, this is a series circuit. So the sum of these two voltages is the same as that. And the resistance of this goes down, which means less energy is required, less potential difference is required to push those electrons through. So, again, as this is a series circuit, V total is V1 plus V2, etc. Right? And the current is the same at all points. So, if the resistance of the LDR goes down, then the potential difference required to, and I'm going to put push here in inverted commas just for the sake of brevity, to push the same current through the LDR. That's also going to decrease, so the reading on the voltmeter, and because I've labelled it as V2, I'm going to put V2 there just because I've scribbled all over this, will decrease. There we go, right. So effectively, if it takes less energy to push the same current through that, then the voltmeter reading on that's going to be higher, and because the so that's going to be higher, that's going to be lower, because the overall voltage is the same. Right, so if I break out the mark scheme for that and have a quick look, this is a level of response one. For a level 3 or 6 marker, I want the relevant points, causes and reasons identified, given in detail and logically linked. So indicative content, let's have a look. The resistance of the LDR changes when light intensity changes, and when light intensity increases, it decreases. So I've said that. Marvellous. What else? The overall resistance decreases, which I have said. I have indeed. And the potential difference remains unchanged. Yep. And so the current on the ammeter increases. So I've got quite a lot of indicative content in there. Right, so I've explained that and what that does. Right, let's move on. The potential difference is shared between the components in series, which is what I've said. The lower the resistance on the LDR, the smaller the share of the potential difference, which is what I've said here. And so the reading on the voltmeter decreases. Marvellous. So that is pretty much a model answer there. That covers everything. Right, this is a particularly challenging question. Right, both of these questions here are particularly challenging in that you need to really understand the difference between series and parallel circuits, and you need to have remembered all of those relevant equations. So hopefully that's given you a good overview of what a science paper looks like, and how you tackle each question, how you tackle long answer questions, how you tackle calculations. Right, thank you very much for your time. Thank you for making it this far. Well done, ladies and gents, and I will hopefully see you all soon.